We just chart the progress in the scientific method. The observation was first that what was the observation that led to the development, ultimately of quantum mechanics? Quantum mechanics is our theory. Quantum mechanics and the Schrodinger equation. And so this chapter deals with some of the history and development of the quantum mechanical model of the atom. So it started off, this is our currently accepted modern day theory, basically. Theory. Theory of what? This is the theory of chemistry. This is the underlying description of the properties of matter, both chemical and physical properties of matter, based quantum mechanics. And so, talking about the development of quantum mechanics, it came from the observation of what? This is just review. The energy levels of. How did they observe the energy levels?
Light.
Of the light, yeah. And so what the observation was is the H atom emission spectrum. What did they expect and what was observed? The hydrogen would be a black body emitter, emit white light. What they observed was it wasn't a black body emitter. All energies are allowed. Basically, it's a continuum. What they saw was that there were allowed energies and forbidden energies, and so we call that quantized energy levels. And actually, it's not just the hydrogen atom, but helium, etc., showed these what we call line spectra. Line spectra show very distinct energies that are allowed, and most of the other energies are forbidden. And so we have the hydrogen, and that was the observation. And then, you see the pattern, which can't turn into law. What was the law we got from this pattern?
Energy levels.
What was the name of the law that we got from this? Or the name of the equation? Rydberg. This is the Rydberg equation that we got. Rydberg, the problem with the Rydberg equation is, well, we'll talk about that in a second. Then it went into, some hypothesis. Hypothesis is that, what was the hypothesis? The hypothesis is that we had orbits, right? Allowed orbits and forbidden orbits. And then this led to the theory, which is the Bohr theory. But the Bohr theory failed, right? The Bohr theory failed. Why did it fail? Because the Rydberg equation and all this orbit stuff could only predict the allowed energies for one electron species. And so the Bohr theory failed, orbits failed. Rydberg is still okay because Rydberg is just an empirical equation that fits the pattern, right? And so it works for hydrogen atom and it works for one electron species. So whatever theory we end up with should be able to derive the Rydberg equation from that theory. And in fact, from quantum mechanics, you can generate the Rydberg equation. The Rydberg equation works for one electron species only. And from quantum mechanics, we can see that. Now, if we have multi-electron species, the calculation gets a bit more complicated. And so what happened between Bohr theory and modern quantum mechanics was, one, we have to do the wave properties of matter, right? What was that? Who's that? Credit to, or attributed to, or whatever. What was that guy's name? He has an equation named after him. De Broglie. And then, two, we have to understand that if we pinpoint the energy, then the position of the electron is going to be uncertain. And what was that called? Heisenberg uncertainty principle. This is just a, well, let's talk about both of these in just a little bit more detail. The Heisenberg uncertainty principle. And with these, then the modern day quantum mechanics. The idea of allowed and forbidden energy is still carried over, but this idea of orbits is wrong. It's a Heisenberg uncertainty principle. Now, let's first talk about the wave properties of matter. And bring this up. Waves are naturally quantized, it turns out, standing waves. So let me show you what I mean. Standing waves would be like waves on a musical instrument. Something like that. Turns out that what de Broglie is saying, is that all matter has wave properties. So when we look at de Broglie, we can determine what the wavelength of that is by looking at the mass and the speed. So the Broglie equation says lambda, or matter, is equal to h over mu. And so we can determine wavelengths. And so, for example, an electron will have a wavelength. We can calculate the wavelength of an electron. We'll calculate it based on a homework problem. Let's say an example would be, what is the wavelength of an electron? Lambda matter is equal to, for an electron with a velocity equal to, let's go with 3 times 10 to the 7th meters per second. So it'd be like 1/10 the speed of light. So what would be the velocity of that? So let's go with the Broglie here. So the calculation, we'll just say wavelength of matter is equal to h. You don't have to memorize h, but once you use it so many times, it's not so hard to memorize. 6.626 times 10 minus 34.
Sorry to interrupt you, Rob. All lights have to be out.
I'm sorry?
All lights have to be out.
Why?
Lockdown.
Lockdown? Oh, okay. All right,
10
thanks.
minutes.
Okay, thanks. Is it a drill?
Yeah, that's happening today.
Okay, thanks. I forgot about it. There's a drill. If it's a drill, then we'll just continue on. Is that okay?
Is that negative 34?
Negative 34, yeah. 10 to the negative 34 joules times seconds, divided by the mass. The mass of electron was 9.01 times 10 to the minus, what is it, 10 to the minus 28 kilograms? 10 to the minus 31 kilograms. 10 to the minus 31 kilograms, I think it is. No, I can look at that. But that number you don't have to memorize either. It'll be given. So, mass of electron. Ten to the minus 28 grams, so 10 to the minus 31 kilograms. Be at 9.11 times 10 to the minus 31 kilograms. We use that for the mass of electron. 9.11 times 10 to the minus 31. Kilograms. And then the velocity, we just chose the velocity, 3 times 10 to the 7th meters per second. And so let's take a look at the numbers here. Units, well, joules we know. What's the definition of a joule? Kilogram meter squared per second squared. So kilograms cancels. One of the meters per second cancels. Seconds cancel, and that leaves us with meters. And so what would that be, meters? I wonder if I have to turn off the projector too. Do I have to turn this on? Oh, hopefully not. Until somebody says something. So I just punched out the numbers. I get 6.626 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 divided by 3 times 10 to the 7th. And, what do I get? 2.42 times 10 to the minus 11. 2.424 actually. Well, I've only got one there. 2.424 times 10 to the minus 11 meters. That's equal to, what is that equal to? That's equal to 24.2 times 10 to the minus 12 meters. 24.2 times 10 to the minus 12 meters is called a what? A picometer. And so this would be 24.2 picometers. Well, 24.2 times 10 to the minus 10, that would be 0.24, right? 0.24 angstrom, or 0.24 angstroms. What do you know about that size? 24 picometers. What does that sound like? Is that bigger than an atom? Smaller than an atom? About the same size as an atom? The wavelength. Just a little smaller, right? How big are atoms roughly?
100 to 600.
Yeah, 100 to 600 picometers, or 1 to 6 angstroms or something like that, right? And so this wavelength is about on par, just a little smaller than an atom. Well, that's going to have important implications. Whereas, let's take a look at something else. Let's take a look at, not for an electron, but let's take a look at the wavelength for a baseball. How fast do you want to make the baseball? Let's make the baseball at 60 miles per hour. How many meters per second is 60 miles per hour? .8 meters per second. I don't want to do the calculation. 26.8 meters per second. And how much does a baseball weigh? Does somebody know? I don't know. It's in the homework, I'm not gonna dig it up. 145 grams of 0.145 kilograms. What's 0.145 kilograms? So, look at this and then go to the de Broglie equation. Lambda of matter is equal to H, 6.626 times 10 to the minus 34 joules times seconds, divided by the mass, 0.145 kilograms, 26.8 meters per second. And so this will give us the wavelength in meters. So we already did the units for this, so the units should work out. So let's take a look. 6.626 times 10 to the minus 34 divided by 0.145 divided by 26.8. 1.701. 1.705 times 10 to the minus 34 meters. 10 to the minus 34 meters, you know. What kind of light is 10 to the minus 34 meters? Didn't that kind of rings a bell? Didn't we look at that earlier? Didn't we have something like that? The number is kind of similar to that photon we were talking about. Remember the megaphoton? Yeah? Wasn't that on the other? That was like 10 to the minus 32, 10 to the minus 32 meters. That was a megaphoton, you know, kind of end of the world type photon. It packs way too much energy. It's like down here. So what is this? Is this a megaphoton? Yes? And what kind of light is this? Well, if it has a wavelength of 10 to the minus 34 meters, then it must be like a gamma ray or something like that out here. Is that correct? Is it true? Yeah? No? Okay, if you say no, why not? Somebody know? Why not?
Isn't it similar to yesterday's with carbon bond?
Yeah, carbon-carbon bonds, kind of like that. Yeah. Where we calculated the wavelength, right? The wavelength was UV. It was 344 nanometers or something like that. UV. 344 nanometer wavelength UV. So if you have a wavelength of 10 to the minus 34 meters, is it okay? Okay, thanks. Jose, can you just hit the lights behind you? It's okay now. 10 to the minus 34 meters, what kind of light is that? Well,
Maybe just higher energy gamma rays.
higher energy than gamma rays? Well, the situation is that this is not light, actually. I'm not allowed to compare it to this chart here. I can't use this chart. because these are the wavelengths of matter. This is the wavelength of light. The difference between light and matter is this. Matter has mass and occupies space, right? Does light have mass and occupy space? Light has no mass, no rest mass, right? Light has no rest mass, and does it occupy space in the sense that there's a volume for each photon? No, each photon has no volume. There's no rest mass, no volume. This is energy. This is different. This is matter. We're talking about this. And so the way we visualize this is this. Here's an electron. An electron's a piece of matter, right? And the electron's going to be moving. When it moves, it's going to have wavelength. The wavelength is going to be the peak-to-peak distance, and it's going to be 24.2 picometers. Here's a baseball. A baseball is going to be moving, and its wavelength is going to be so small. It's 10 to the minus 34 meters. 10 to the minus 34 meters, what is that? That's like nothing. Well, what implications does this have? The implication it has is this. When we look at waves, like for example, the waves on a string, we see that the waves on a string are quantized here. If you look at this, they're quantized by half wavelength. In other words, we can fit a half wavelength here. So if you pluck the string, it'll vibrate at this, whatever this energy is, a frequency or sound. But the next energy is, you have to plug it quite a bit harder to get, because the next energy is going to be twice that. In other words, we could fit 2 half wavelengths in here. But we cannot fit like 3/4 of a wavelength or whatever. And so what we're going to see is that when we look at the mathematics of this standing wave here, it's going to be based on half wavelength. This is the equation for the wavelength. But anyway, we can have multiples of half wavelengths. Those are allowed. And so we could have 1 half wavelength, although we're looking at the wavelength here, but we should, look, it's n times the lambda. So we could have 1 half wavelength. And so n is equal to 1 here. We could have 2 half wavelengths, n is equal to 2. But could I get 1.5 half wavelengths in here? No, it's impossible. And so every other half wavelength here is forbidden. And so this, the first allowed one is 1, the next allowed one is 2, the next allowed one is, we can predict is 3 half wavelengths. The next allowed one would be 4 half wavelengths. But if I try to put in an n equals 1.1, it's not going to work, or an n equals 1.5, it's not going to work because it just doesn't fit in there. And so, I mean, it's pretty much impossible to get 3/4 of a half wavelength in there, because 3/4 of a half wavelength would be here, and the string's supposed to be attached here and here. It's not going to work, right? So this is what we call forbidden energy. That's a forbidden energy. And so when we have waves like this, we have, allowed energies and forbidden energies. Now, imagine an electron. An electron stuck inside a box like this. If an electron stuck inside a box like this, then what we can think of, the electron is going to have quantized energies as well, because for the electron to exist in this box, because of its wave properties, and we'll talk about the wave properties of the electron a little bit more, but you have to just go with this now. If an electron's stuck, and so this is an electron, An electron's wavelength, let's say, is 24.2 picometers. And so what we can do is we can fit, you know, 1/2 wavelength. Let's say the electron is in the box. We put in 1/2 wavelength here. That'll fit in the box. But the next allowed energy, well, the next allowed energy is going to look like this. You know, the next allowed energy here. Let's say the box has this dimension here, so we can fit that in there. The next allowed energy is going to be where we get 2/2 wavelengths in there, right? And so this is going to be higher energy, right? Here. The next allowed energy is when we get 3/2 wavelengths in there. And so the half wavelengths are going to be 12.1 picometers. At least, well, this is going to be at 12.1 picometers, so whatever we can fit in there. So those are going to be the allowed energies. What's going to happen is this. If we go back to earlier slide, let me go way back here. When we're looking at waves, we have two types of interference here. You know, we have constructive interference and destructive interference like this. And this constructive and destructive interference, we can see the wave properties of an electron. Although this is not in your book, maybe I'll bring this up here. But if we go to the famous double slit experiment, and we look at the animation. The double slit experiment is like this. Think of water waves. See how waves interact. When we think of water waves, and it hits a wall, and there are two slits in the wall. So we have some waves, water waves coming this way. The waves are coming this way. And so let's say this is a wall or barrier. And what's going to happen is the waves are going to go through this wall or barrier. As they go through, they're going to go through this and they're going to spread out in this fashion here once they go past the wave. And the same thing here, they're going to spread out like this. And then when you see the waves come together, like this wave front and this wave front come together, then we're going to see areas of constructive interference and destructive interference in those water waves. And so I think there was a figure of this. It's similar to this, not exactly the same, but here what we would have is the wall here. And then the waves would be originating through the two holes in the wall. And then do you see this pattern here that arises? This pattern is from interference pattern where we have constructive and destructive interference of the two waves. And we get this distinct pattern here. Do you see that? Okay. And so I can see that here spreading out from this. Well, that's water waves. The double slit experiment is with electrons. So if you shoot an electron, you know, one electron through here, what would happen? Well, if we shoot one electron through here, it could either go through here, right, or through here. So you put a detector and detect it. It goes through here, bing, detector here, one electron, right? And so if we have one electron is a piece of matter. And so, you know, it could go through here or here. But could one electron go through both holes? Is that possible for one electron to go through both holes? Well, if one electron were a wave, if an electron were a wave like this, then yeah, it could go through both holes because it's just a wave, right? But if one electron is like a particle, then it's going to go through one or the other. Right? And so what is an electron? Is an electron a wave or is an electron a particle? Let's see. A little more of this little animation here. use this guy to explain it. What is this? The volume here. Oh, sorry, let me, try some. Okay, somebody had changed the audio on this. We'll just look at it. This is a water wave passing through a slit. Well, basically, let me just tell you what happens here. Basically, the electron's a very strange thing. You know, whatever you think of the electron, whatever you think about the electron, it's not right, because electron is like impossible to describe, because on the one hand it behaves like a wave, like these water waves, and so when one electron shoots here, you get an interference pattern like we get with the water waves. This is the interference pattern here. Interference pattern would be constructive, destructive, you know, how the waves interact. And then on the other hand, it's like a particle, you know, when it hits, it'll hit the detector. And so it's very strange. And the electron, there's no, you know, there's nothing that you can imagine that it's similar to in our world, you know, in thinking. And so electron is something that's very, very difficult to describe, because you know, some people say it's both a particle and a wave, but it's neither a particle nor a wave, and so there's nothing like it, an electron. Here, well, you know, with the new atomic physics, you know, then it makes more sense, you know, what a particle is, what a wave is. You know, when you have these Higgs boson things picking up mass as these things travel through space, or these fields. But we aren't going to get into that. What we're going to do is we're going to talk about the implications for the electron on the atom. And so if you think about the wavelength there, the wavelength is about 24, which is smaller than an atom. An atom is about what? how big is an atom roughly? An atom's about 100 picometers or so. And so if you got an electron there, then the wavelength of the electron is kind of comparable, or it's significant to the size of the atom. Right? And so what we do is we don't imagine an electron in a box. We imagine an electron in an atom. But when we have an electron in an atom, then what's going to happen is, wow, they're going to be forbidden wavelengths and allowed wavelengths. And that is, this would be a forbidden wavelength because it's just a little bit too long. A little bit too long, we're going to get destructive interference with an electron that's stuck in this atom here. And so this one is going to cancel itself out because eventually, if it's just offset a little bit, we're going to have destructive interference. And it just has to be offset a little bit. Whereas this would be a proper standing wave. This could be stable in this sense. And so standing waves are quantized, just like electrons are quantized in matter. If we think about the wave properties, and so this is a reason given that there's going to be forbidden and allowed energies because of this problem here. And so the difference is we don't see it in terms of a baseball. Because in terms of a baseball versus in terms of electron, in terms of electron, we imagine an atom. An atom's dimension is kind of small. The wavelength of an electron is kind of big. And so this would be forbidden. However, this would be allowed. Have something like this. This would be allowed. It's just because of the atom. So let's call this about the size of an atom here. Now, if we have a baseball, it's going to have to meet the same restrictions. Baseball is a wave. But when we think about a baseball, let's say there's a catcher over here. Well, how many half wavelengths do you think I can fit between the pitcher and the catcher here? How many half wavelengths? What's the distance? This is pretty long. And the half wavelength is so small, even way smaller than an atom, right? The half wavelength is way smaller than an atom. So what's the next allowed energy? The next allowed energy is, let's say I have some crazy number, like trillion half wavelengths in there. Well, the next allowed energy is a trillion half wavelengths plus one half wavelength. Well, how big of an energy gap is that? So to go from trillion to trillion and one, is that a big jump in energy? No, that's barely any gap. Just to fill another half wavelength in there, well, it's got to be moving a little bit faster. But how much faster is that? Probably imperceptibly faster. Whereas this one, to jump up to the next one is a big jump because all of a sudden we've got to do that, right? And so we're going to see big jumps here in energies. Whereas this one, we are not even going to see a jump in the energy. Okay? And so the analogy goes here. Let me just do this analogy for us. The implication is like this. If I have an iron atom, then what I'm going to see is quantized energy levels. Like, for example, the electron can be here, and then there's going to be a jump in the energy here. Because in an iron atom, the same thing's going to happen. I have some nucleus here, and then I got to fit the half wavelengths in there, right? And so in an iron atom, we're going to see quantized energy levels, and what we're going to see is a line spectrum. If I look at the spectrum for iron, I'm going to see distinct lines in there. Boom, boom, boom. And then these are allowed. This is forbidden. And so an iron atom's like this scenario here. But if I have a piece of iron metal, if I have iron metal, then what happens is the electron, is the electron fixed on one atom in the iron metal, or can it move from atom to atom? It can move. In fact, if I have iron metal, the electron is kind of free to move about depending on how big this block of iron is. And so now when I think the electron is free, this is called almost free. This is an almost free electron, almost free. And if the electron's almost free, then it's free to move over the entire chunk of iron. And so the entire chunk of iron can be pretty big, you know. Like, can you count how many atoms there are from this end of the iron to that end? It'd be like a trillion atoms, wouldn't it? Something like that, some enormous number of atoms from here to there, correct? And so what's allowed then is electron can have this energy. Well, you know, all of a sudden I got trillion atoms. This wavelength looks awfully small here compared to the size of my iron block. And so what this is like this. Iron metal will be a black body. Iron atoms will not. Iron metal will be a black body because this one, the next allowed energy is a trillion half wavelengths plus one, which is barely any higher in energy than this. And so even though it's quantized, it looks continuous because the gaps between the energy levels are so small, they're imperceptible. And so iron metal behaves like a black body. Somebody asked me about the sun. You know, why isn't the sun emitting? The sun is mostly hydrogen and helium, so why isn't it emitting line spectra like that? And then the reason is because, you know, in the sun there are what we call free electrons. If you're a free electron, you know, moving in space, then it's like this. You know, if you're a free electron moving in space, then any energy is allowed. A continuum of energy is allowed because to bump it up is just another half wavelength above this. And so free electron in space has lots of room. Whereas if you start to shrink it down and confine that electron into a tiny box, then all of a sudden, that tiny box, it's constrained, you know? It doesn't have free movement. And so if you're a person in a crowded room, you're going to be constrained. You don't have free movement. But if you're a person in an empty room, you can move any way you want, right? Any energy's allowed, any position's allowed. But once you're crushed down into a tiny box, then things become constrained. And so this is why people think of quantum mechanics. When they think of quantum mechanics, they think of very small objects, because very large objects, even though energy is quantized, very large objects, you don't see it because it's pretty free. And so all the equations of classical physics are not wrong. You know, the classical physics is if you assume large objects, then we don't have to worry about the quantization of the energies here because it's pretty much a continuum. But when you shrink it down, then all of a sudden it becomes important. Does that make sense? And so baseball, who cares about the quantum properties? Nobody, because they're negligible. That wavelength, if you try, 10 to the minus 34 meters? Nothing. It's nothing. Okay. So there's actually, this one we don't need any sound for. I don't know what happened to the sound. But do you want to see, we see quantization in a lot of things here. And so that was a string, but let's take a look at some 2D standing waves. For example, on the surface of a drum, using anything like that. Here we can see 2D standing waves, like for example, this would be allowed. You know, here's some allowed ones. You see those? Allowed energy state. This is an animation. We could do this. This is something that people do. They use the sound here, vibrations, so you could see. This is water, it looks like. But we could also do metal filings. That's kind of interesting. This is hard to see. Do you see the patterns that come up? Those are hard to see. There's better one. There's a better one. Give me those. I don't know what it's doing here. This. I get too many ads. I don't know why this came out. It usually comes right out, so that's why I don't. Alright, this is a little easier to see here. The one I usually show. Actually, not this one, but didn't have the monkey drawing. The pictures there. You see, you change the frequency of the plate. So if the audio were working, you could hear it vibrating, and it would be vibrating at different energies. And so these are just showing the loud energies there. So there'd be no vibration as we jump from a loud energy to a loud energy. And so I'm gonna kind of fast forward this, taking some jumps here. So you can see different allowed energies. You go higher and higher energies, you get these different patterns that result from the 2D standing waves. And so that's allowed, and then they'll turn up the energy here, and go through a forbidden region, and then again, they'll hit an allowed region. And just cranking up the energy. So forbidden energy, nothing's happening, then all of a sudden, we'll hit an allowed energy and something happens. You see, something happened there. It's allowed energy. And forbidden. And so we'll just scroll through some of the patterns there. Those are 2D standing waves here. Okay. And there are lots of these. This is. So maybe this one has better. Yeah, this is probably better. So there is an allowed. Crank it up. This one they can get higher energies. So let's take a look at some of these other ones. There. There, that's an interesting one. What does that look like? Looks like a p orbital, doesn't it? This one looks kind of like a d orbital here. F orbital. Wow. That's a cool pattern. All right. And so we see a quantization occur in all this stuff. That's because here the wavelength and the plate are about comparable in, in size. All right, so here, just showing you. Let's go back up a little bit. Let's talk about the Heisenberg uncertainty principle. Heisenberg uncertainty principle it comes from the process of observation. They say, it's like if you're a photographer trying to use
a camera at an intersection. You know, are you familiar with like shutter speed and that kind of thing? Okay, if you're at a busy intersection, you could take a picture, and it would freeze everything, right? And so you could see the position of everybody, but could you see how fast they're moving? No. The other way you could observe this is if you take a very long exposure, and so what you see is a blur. But if you see a blur, you can kind of see, you know, how fast people are going, but you can't pinpoint the position. Well, you probably could with time, whatever, but, you know. And so the same thing happens with like electron. You know, to observe an electron, you have to shoot a photon at it. When you shoot a photon, you can pinpoint its position, but you can't determine where it was coming from, where it's going, right? That's the same kind of problem. Or you can pinpoint the energy, but you can't figure out its position. Well, we're going to pinpoint the energy, like I said. We're going to figure out the position. This is an uncertainty principle graphically. But we'll skip that. We're going to skip some of this stuff in here. Here's a Schrodinger equation. Schrodinger equation has this H here. HXYZ or HR theta phi. But you know, this isn't the whole equation. This is just Schrodinger equation H. And the answer is actually more than this. So this is not really showing the Schrodinger equation. H is what we call the Hamiltonian operator. But you don't need to know that. What you do need to know is that we have an equation which is not shown here. And this is the answer to the Schrodinger equation. The answer to the Schrodinger equation are the allowed states of the electron. So for the hydrogen atom, if you solve the Schrodinger equation, you'll get an infinite number of answers. But each answer has to fit a certain number of constraints, which deals with N, L, and M. This is showing R theta and phi. R theta and phi is there's two parts to the Schrodinger, the answer here, and that is you know, where the position is, radial and angular function, the energy. But essentially, what we focus on are each psi, and psi is called a wave function. Each wave function, or it's also called an orbital. We'll just say each orbital. Each orbital is going to depend on three quantum numbers, N, L, and M. Which I mentioned yesterday, but N is what we call the principal quantum number. The principal quantum number tells us pretty much the energy of the electron. 1 being the lowest energy, and we go up higher in energy. L tells us the shape of the probability distribution and the energy as well. Because increasing L will usually mean increasing energy, usually. And so L equals 0 is spherical. L equals 1 is what we call a p orbital. L equals 2 is a d orbital. And so we give letter designations to these. This is S orbital, p orbital, d orbital. Now, the S, the p, and the d will have slightly different energies for multi-electron. This is shown here. Oops. So L equals 1 is an S orbital. I'm sorry, 0 is an S, 1 is a P, 2 is a D, 3 is an F. What is 4? What kind of orbital is 4? L equals 4. S, P, D, F. If I had an L equals 4, is L equals 4 allowed? Yes, L equals 4 is allowed. What kind of orbital is it? I think we ran out. What did you learn for orbitals? Did you learn about the S orbital, the P orbital, the D orbital, the F orbital? Yeah, L equals 4 is the G orbital. L equals 5 is the H. And so just go alphabetical from then on. And then we have the magnetic quantum number. The magnetic quantum number tells us the orientation and the number of orbitals. Orientation and number. And so we could figure these out. Now for each L value, we're going to have this. For each L value, how many M values do we have? Well, we can let's figure out some mathematical relationships between the quantum numbers now. And so I told you there's some mathematical restrictions of the quantum numbers. These are the mathematical restrictions of the quantum number. And so now I'm going to ask you to look for new patterns. For each N value, how many L values do we have? Can you tell? For each N value, how many L values do we have? So if N equals 1, what are my allowed L values? Well, it'd be 0 and up to a max of N minus 1, so it would just be 0. So for each, well, okay, what if I had N equals 2? How many L values are allowed? If I have N equals 2, then 0 is allowed? Yes. Is 1 allowed? Yes. Is 2 allowed? No, 2 is forbidden. If N equals 3, what are my L values that are allowed? 0, 1, 2, how about 3? Do you see a pattern? We always look for patterns because these are easier to memorize. What is the pattern between N and L? For each N value, we have how many L values? N. And so for each N value, we have N L values. And that is, if I had N equals 50, how many L values would I have? 50. If I had N equals 10,000, are you going to sit there and count them? No. You can just figure out based on the pattern how many L values I'm going to have. 10,000. And so these kind of things we want to know. Now for each L value, let's say L is 0. What are my allowed M values? So if L is equal to 0, then I'm allowed from minus 0 to plus 0. In other words, I have 1. If L is equal to 1, then I go from minus 1 to plus 1. So that would be minus 1, 0, plus 1. That's 3. If L equals 2, I go from minus 2 to plus 2. So it's minus 2, minus 1, 0, plus 1, plus 2. That's 5. Can you tell me the mathematical relationship between L and M? So if L equals 10,000, how many M values do I have? If L equals 10,000, how many M values would I have? It'd be 20,000, close. 20,001. Do you see the mathematical pattern? If L equals 1,563,000, how many L values would I have? Well, I just double it and then add 1. And so the number of M values that I'm going to have is 2L plus 1. That would be the mathematical equation relating to that way. If I, we can see that here. And so if I have L equals 0, I'm going to have 2L plus 1, this is just one value here, and that would be M equals 0. L equals 1, I'm going to have 3 values. Plus 1, 0, minus 1. L equals 2, I'll have 5 values of M. Plus 2, plus 1, 0, minus 1, minus 2, etc. And we can figure out the values. And so, in other words, this is it. If I'm in L equals 2, I have 5 values. Each of those values is called an orbital. So we have 5 orbitals in L equals 2. We call it a subshell. This L equals 2 is D, so I have 5 D orbitals. Okay? Let me ask you a question. How many H orbitals are there? How many H orbitals are there? 11's correct. Does everybody see that? First, you have to figure out what L is H. Well, 4 is G, so 5 would be H, and then we know we have 2 times 5 is 10 plus 1, 11 orbitals. We should have 11 H orbitals. Right? 11 H orbitals. Some people. So these are what we call subshell. You know, L would be the subshell, and we have different numbers of orbitals in the subshell. The S subshell, the P subshell, the D subshell, the F subshell, the H subshell. So if we look at this diagram here, this is the energies for one electron species. For one electron species, the subshells have the same energy. So if we have one electron, then an electron in a 2s has the same energy as an electron in a 2p. That's because this. The 2s and the 2p have the same effective distance from the nucleus. Effective distance would be, you know, they have different shapes, but when we normalize it over a 3-dimensional sphere, it comes out the same. And so, here, this is the equation we just derived, 2L plus 1. But the energies of one electron species just depend on n. The Rydberg equation holds here, so E1 is minus 2.179% minus 800 joules. This would be 1/4 of that. And both the 2s and the 2p have the same energy. And the 3s, the 3p, the 3d have the same energy. Is there such thing as a 2d? Am I missing the 2d? The 2d is forbidden, right? Because that would violate the L. The maximum L would be this one, 1. And same thing here. So we can figure out what's allowed. When we go 4s is allowed, 4p, 4d, and 4f is allowed. And so this is one electron species. But before we do that, let's take a look at these. This is an angular and the radial part of wave functions for hydrogen. And so when you solve the Schrodinger equation, you can come up with these. These are the answers to the Schrodinger equation, but not the full set, you know, because there'd be an infinite set. You know, and we just go through it systematically. But this we don't have to do anything with. We just look at it and say, okay. It turns out that the Schrodinger equation is easy to solve for the hydrogen atom. And so we could derive these equations pretty easily if you've had differential equations in calculus. If you have differential equations, then this is not hard. This is easy. But any atom beyond 1 electron is like impossible to solve using the Schrodinger equation. It's impossible to solve, so what you do is you use approximations. And by using approximations and assumptions and this kind of stuff, you can solve them some reasonable answer. Well, let's take a look at the wave functions. This one, I'll kind of skip this one too. But the angular parts can tell us the shape. So this is the s orbital, spherical. This is p orbital. And we have 3 p orbitals, the pz, the px, and py. Those would be labeled with different quantum numbers. And then we have d orbitals. And we have 5 of these d orbitals. These are the shapes. Now the shapes are given different things. The blue, which is positive, these are waves, so the blue part is positive amplitude. And so the blue part, this is positive amplitude. You can imagine this part of the wave sticking out. And this is negative amplitude. You can imagine this part of the wave sticking in. So it comes out and then back. And same thing here. And you can see here, these parts would go in, these parts would come out, amplitude-wise. And so that's the amplitude. Let's take a look at the waves here. This is a wave here. This is an S, and so you can see it's positive amplitude, so this is giving the positive there. This is the wave function in 3-dimensional space. What does this represent? here you can see it here. What this represents is different things. This is a loud state, so this energy is allowed for the electron in three-dimensional box, like something like this here. Spherical, we plotted out in 2D, 3D problem like this. Okay, now, this is the wave function, so this is a loud state. Now, if we square that, we get the probability function. We have to square it because we don't want negative probabilities. In this case, we don't really need to square it, because we would get positive probability. But psi squared, psi is the loud, so this is a loud state electron. The loud state electron is both energy and position. Psi squared is the probability. This tells us the probability of position. And so you can see the highest probability will be close to the nucleus, which is in the center. And then the probability of finding the electron drops as we get further and further away from the nucleus. But the probability doesn't go to zero until we hit when? Until we hit r equals infinity. So it's going to be a very, very small probability. Well, that probability is so small that we don't worry about that necessarily. What we worry about is either 90% boundary or 95% boundary. Do we use 90 or 95? It doesn't really matter yet. But what we're going to do is, if we look at the volume of this peak, we want to capture like 95%. And if we capture 95% of that, then we have 95% probability of finding it within this volume. And so that's what this sphere represents. The sphere represents this, let's say, a 5% probability of finding it outside the sphere, and 95% probability of finding it inside the sphere. This is what's shown in space. You know, the electron, this is electron, what we call electron cloud. You can see the denser the cloud, the higher the probability. The lighter the cloud, the thinner the cloud, the lower the probability. And so for the probability of finding the electron in space is here. This is because we're pinpointing the energy. If we pinpoint the energy, then we don't know the exact position of the electron. Even though we don't know the exact position, we do have a probability of finding that electron in there. So it can't be just anywhere. It's most likely going to be here in this volume. Okay. Now, if we go higher energies, then this is what we see as far as the probability boundary. What we're going to see here is this. When we go to the next higher energy, it's going to be positive amplitude, then it's going to drop down to negative amplitude, and go back to positive. So it's going to look something like this. It looks zero. Yeah. And so this is why we see positive amplitude here, negative amplitude. Now, when it passes from positive amplitude through zero to negative amplitude, we call that a node. Nodes, the wave has zero amplitude. And so the next higher allowed energy is going to look, so we go here, this is the first allowed energy. This is, we call this psi. And in this case, N, L, M. Okay, this is psi 1, 0, 0. That is, N is equal to 1. If N is equal to 1, L is equal to 0, and M is equal to 0. So this is the lowest energy orbital. Now the next higher energy orbital will be the 200 orbital. 200 orbital is going to be, something like this. Okay, this is called a node here, where it goes through zero amplitude. Zero amplitude for the wave. And so when we go past from positive to negative here, we're going to go through a node, and the node is going to be the boundary between the positive amplitude and negative amplitude. When we look at the probability, here you can see how many nodes here. This one we're going from positive amplitude to negative amplitude to positive amplitude, and back down to zero at r equals infinity. How many nodes there? Two. So do you see a pattern in the nodes? Let's say I went to the 1000 s orbital. If I go to the 1000 s orbital, is the 1000 s orbital allowed? Is there such thing as a 1000 s orbital? No? Well, how many orbitals are allowed for the hydrogen atom? what's the maximum n value I can have? What's the maximum n value? Do you know what the maximum n value is? Infinity. So is 1,000? Sure, 1,000's a lot. So I could have 1,000 s orbital. How many nodes? Take a guess. How many nodes? I would guess 999 nodes. Right? Do you see the mathematical pattern? They're going to be n minus 1 internal nodes. Internal nodes, there's always a node at r equals infinity, because that's where the amplitude drops to 0 at r equals infinity. So that's called an external node. If there's n minus 1 node, internal nodes, sometimes you'll see it as n total nodes. What do the wave functions look like? Well, I don't have a picture of this one. I do have one for the p orbital, though. This is a p orbital here. P orbital, you can see here. With negative amplitude, positive amplitude, psi, this is loud. This is the 2, 1, 1 orbital. 2, 1, 1 orbital. The wave function. For the wave function, we have to keep track of the negative amplitude and positive amplitude, because the waves interact. Waves interact with each other. So if you have negative amplitude and positive amplitude, do they interfere constructively or destructively? Destructively. We need positive amplitude with positive amplitude, or negative amplitude with negative amplitude. It's called the phase, the orbital. That's important because when we form bonds, we got to form it positive with positive. We can't form positive with a negative to form a bond. And that's going to have an impact on the structure, the three-dimensional structure. And so this is why we color code these, red and blue, like this. But essentially, this is the wave function. This is what it looks like in three-dimensional drawing. And this boundary here is not a hard boundary. It's just a boundary showing that 95% of the curve is inside, 5% is outside of the volume. And so we have 95% probability of finding an electron within the volume, either side. Yeah. And where the wave passes from negative to positive amplitude, that's called a node. Now we have different names for the node. This is called a planar node. A planar node, plane. What would you call the earlier node? Well, you certainly wouldn't call this a planar node. You'd call it a spherical node. It's a spherical node. And then there's one more type of node that we look at. It's a conical node. Looks like an ice cream cone type node. But anyway, here is the probability function. Why we square it is because we don't want negative probability. Probability is always going to be positive. So we have equal probability either of these nodes of finding an electron. It's at 95%. And so the p orbital is going to look something like this in terms of the electron cloud, in terms of finding the electron. This is an allowed state. So this is an electron in a box. This is a allowed state in the electron. We have 3 of these, given by m. Each of these 3 are going to have different m values, and we'll break it down. And they're exactly the same energy, just different orientation. So we have one on the x-axis, one on the y-axis, one on the z-axis. We call it the px, the py, and the pz. Each of those will have 3 distinct quantum numbers. These are d orbitals. D orbitals, how many nodes do you see in d orbital? These are 3D orbitals. So if it's a 3D orbital, how many nodes do you have? N equals 3, how many nodes? You have 2 nodes, n minus 1 node. And so this one's going to have 2 nodes. One planar node slicing it here, and another planar node slicing it there.
1, 3. You can see that. Note there's zero probability of finding an electron. We find them in the lobes here. Here, there are two nodes, but these are conical nodes. There's one ice cream cone coming up here, one coming down here. Two ice cream cones. Stuck. This side. You can see the nodes here. This is a planar node, conical node. This is called the DZ squared orbital, which has a little hula hoop here. Looks like a p orbital, but this is all one orbital. Positive amplitude, negative amplitude. See that? So these are allowed. These are all the allowed states. So not all, because there are a heck of a lot more. These are the wave functions themselves. When you solve the Schrodinger equation, you get two parts. So this is one allowed part. And then in the wave function, although they don't show it here, there's n, l, and m. And so they plug in an n equals 2, an l equals 0, and an m equals 0 into the equation, and this is what it spits out. And so they look for a pattern in all the answers. The pattern in the answers is broken down into 3 variables, which they aren't showing here. It'd be nice if they showed it, the 3 variables to it. But basically, we don't need to do any math. All we need to know is the pattern. Once we know the pattern, then we can generate. If you had enough time, you could generate the entire energy level diagram for the hydrogen atom. It's not hard. Well, how many orbitals are in the entire energy level diagram for the hydrogen atom? Well, for the hydrogen atom, it turns out that the energy levels are fine. N equals 1, En. This is for hydrogen atom. En is equal to minus R sub h over n squared. So we can figure out the energies, where n goes from 1, 2, all the way up to n equals infinity. And so they're going to be an infinite number. Well, of course, if you had time, you can generate them all, right? It's not hard to generate them all because of the restrictions in quantum numbers. So n equals 1, how many orbitals are in the n equals 1 total? Well, we'll look at the pattern. Well, there's 1. N equals 2, how many orbitals are there? Well, there's the 2, 0, 0. This is 1, 0, 0. This is n, l, and m. And that's it. But if we have 2, 0, 0, we got the 2, 0, 0, which is l equals 0. But we also have the 2, 1. We got 2, 1. And now if we have 2, 1, then we have a choice. We have 2, 1 minus 1. We have 2, 1, 0. And we have 2, 1, 1. And so in the n equals 2, how many total orbitals are there? In the n equals 2, there are going to be 4 total orbitals. Do you see a pattern? Well, maybe you will in the next one. I go up to n equals 3. N equals 3, I'm going to start off with 3, 0, 0. This is L equals 0. This is L equals 1. Well, I can have L equals 1 too. And so I'm going to have 3, 1, negative 1, 3, 1, 0, 3, 1, 1. But now I'm allowed one more L. I can have L equals 2, so I can go 3, 2. Well, if I have 3, 2, then I can go 3, 2 minus 2, 3, 2 minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. Am I allowed L equals 3? Can I have L, I mean, this is L equals 2, but can I have L equals 3? No, that's forbidden. So, okay, now the question is, how many sublevels do I have? Well, here, for n equals 1, I have one sublevel, the s sublevel. This is called the 1s orbital. For n equals 2, I have 2 sublevels, the 2s orbital and the 2p
sublevel. The 2p sublevel has 3 orbitals. The 2px, the 2py, and the 2pz. 2l plus 1 orbital. How many total orbitals are there? How many total orbitals? 4. The n equals 3 has how many sublevels? 3 sublevels for a total number of orbitals of 9. So what's the pattern? N squared. So let me ask you this. In n equals 25, which isn't that far up, because that's still way below infinity. At n equals 25, how many sublevels are there? 25 sublevels. How many total orbitals? So 625, is that right? Okay. Could you figure them out? Yeah, you could figure them out if you had enough time because the pattern. Do you see the pattern? That's all. And using that pattern, we can generate the entire chart all the way to n equals infinity. Because it just takes an infinite amount of time, but you could do it. Not that you'd want to do it. You could do it. All right, this is for the 1 electron species, and then we'll look at multi-electron species. It turns out 1 electron species, all the orbitals, energies, are just dependent on n. So, all 9 orbitals have the exact same energy. This is why in the hydrogen atom spectrum, even though we have lots of different allowed states, it only looks like we have 1 allowed state here. So if we're in the n equals 2, it looks like we have only 1 allowed state because all these have the same energy. And so 2 to 1 drop, or 3 to 2 drop. We have a whole bunch of allowed states, much more than what Bohr had predicted, because we're dealing with orbitals. But since all the orbitals in a shell, this is called a shell, or a level, and in a shell or a level there are sublevels. Well, all the sublevels have the same energy in a level or a shell. All right, so actually I'm going to stop here and then we'll continue this next time.